Okay, question 1 is about Pepper's Ghost. It's a theatre effect used to make it appear as if there's an image on stage. There's a sheet of glass placed on the stage, and a brightly lit actor is standing behind the curtain. Now, what they're asking you to do, is to add a ray diagram to show how light from the actor appears to come from the image. Okay. Now, essentially, the audience is down here, so for them to receive light from the actor, then the light has got to hit the mirror and be reflected off. Okay. Always add an arrow. Okay, and obviously yours should be drawn with a ruler. Unfortunately, I can't do that on here. Now, in order to show that the law of reflection is held here, we should really try and label these angles, I and R. You might even want to write that I is equal to R, just in case our diagram is poor. And then we can continue this line back to show this is a reason why we think there's an image there, is that the light that we receive at our eyes, our brain is telling us it's come in a straight line. So we think that, as the audience, that we've seen the image in a straight line, when in fact the light has come from the actor behind the curtain. So we're looking for 1 mark for showing the reflection, 1 mark for the normal, and 1 mark for then continuing the ray here all the way to the image. The image formed by the glass is a virtual image. Okay, state what that means. Well, what it really means is that no light rays have actually come from that image. You see, we've drawn a light ray in here. Okay, now that is not a real light ray. No light has actually come from that image, and that's what makes it a virtual image. Okay, in a real image, like you might see on a projector screen, light rays actually originate from that image. So no light rays come from the image. Okay, light travels as a transverse wave, but some waves are longitudinal. Give an example of a wave that travels as longitudinal. Well, the main one that we've dealt with is sound. You could equally use ultrasound there as well. And then 3 marks for describing the difference between transverse and longitudinal waves. Now, the waves that you're most familiar with are transverse waves, because that's most of the waves we've been dealing with. Now, transverse waves will have vibrations that occur around a fixed position. Okay, and the fixed position is my dotted line here. Now, the particles will move up and down around this fixed position here in a transverse wave. So we say that the vibrations, and we need to really vibrations, or the oscillations, occur at 90 degrees or perpendicular to the wave direction, or the direction that the energy is going in. Now, there's lots of parts of this that you've got to make sure you include here. You need to be talking about the vibrations or the oscillations. You need to be saying that in transverse they occur at 90 degrees to the wave's direction. Okay, and if you miss those things out, then you're not really fully describing it. When it comes to the longitudinal, we're going to say the same thing. We're going to say vibrations occur, but this time we're going to say that they occur parallel to the wave direction. So instead of saying at 90 degrees, in a longitudinal wave, the vibrations occur parallel. So they're going this way here. In both cases, the wave direction, I'm assuming, is going from left to right. So here it's 90 degrees to that, while here it's parallel in the longitudinal. In question 2, we're looking at an extension reel, and they're asking you to state an equation that links power, current and voltage. Well, PIV, P equals I times V. If you want that in a triangle, then that's P at the top, I and V. A triangle is not acceptable for an equation. You need to put it into one of the forms with an equal sign. Now, we then want to find the missing current. If we've got 700 watts and 240 volts with a cable, well, we want I, which is P over V. There's no marks for workings actually here, there's only 1 mark in total. 700 divided by 240, and we get about 2.9 amps. Now part B is basically just asking us, how does a fuse work? Okay, 3 marks. The key things they're looking for, okay, is that the fuse melts or breaks. The second mark, if it only breaks if the current exceeds a rated value. In this case, it's 13 amps. Okay, and then once that's happened, the third mark is going to say that if the fuse melts, then the circuit is broken. And once you've got a break in the circuit, we're going to get no current flowing. It then says, explain why a 5 amp fuse is not suitable for this extension cable. Well, if we fully extended the cable, if you look at the table, it says it requires 10 amps to function correctly. Okay, now this fuse will blow at 5 amps. So one mark is basically going to say that the fuse will melt and stop the circuit even under normal operation, okay, even before anything gets dangerous or is likely to damage the extension cable, okay, and therefore that means we cannot extend the cable to its full length. It's okay for it to work when it's barely extended at all, but once you pull it out to its full length, we'll get 10 amps and the fuse will blow up. It then says, suggest why the maximum recommended current is lower when the cable is coiled up. Well, it's not going to make any difference to the resistance of the coil, okay, whether it's coiled up or whether it's fully extended. The current is still going to flow through the entire length of the cable. But when it's coiled up, if the cable starts to get warm, it's not going to be able to radiate as much heat energy from it, and it's not going to be able to cool down because it's basically wrapped up in lots of other layers of coil. So basically, we want to have a lower current so that it doesn't overheat. Okay, so if you said something about to prevent overheating. Okay, question 3. We put a toy car on a slope, and the student wants to find the link between the starting height, which is labelled here on the diagram, okay, of the car, and the speed of the car at the bottom of the slope. It then says state the independent variable. Now, from the work you've all done on investigations this year and in previous years, hopefully you all know what an independent and dependent variable is. The independent variable is what you are changing, so that must be, in this case, the starting height. Okay, because we're looking at a link between the starting height and the speed of the car at the bottom of the slope. So the starting height is our independent variable, the speed of the car, that would be our dependent variable. Suggest a link between the starting height of the car and its speed at the bottom. Well, it would seem reasonable that if we increase the starting height, then we increase the speed at the bottom. Describe how the student should measure the starting height of the car. Well, if you look at that diagram, all we're looking for is a distance that we're going to measure here. There's no need to use any kind of trigonometry or anything, which is what a few people suggested. All we're really going to say is we're going to use a ruler to measure that starting height. Now, for the second mark, you need to add something in terms of the experimental procedure, how you're going to improve the accuracy or the precision. Something like make sure that the ruler is perpendicular to the floor. Okay, so you're going to make sure that your ruler is at right angles here. Okay, you could say something about reading the ruler at eye level to reduce a parallax error. Anything like that is reasonable. Now the student describes how she'll find the speed of the car at the bottom of the slope. Start the timer when the car begins to move, stop the timer when the car reaches the bottom, and then use basic speed, distance, time equation. Now you've got to explain why the student will not be able to calculate the correct speed using this method. Well, hopefully you've realised if you put a car on the slope and you let it go, it's not going to travel at a constant speed down the slope. Okay? It's not going to keep the same speed. What we're going to find is it's going to start from stationary, so then it's going to go pretty slow here, and by the end it's going to be going fast. Now if you use the speed, distance, time equation, it gives you an average speed. So 1 mark here is for coming up with that decision that you realise that speed, distance, time gives average speed, and what we want, okay, is the speed of the car at the bottom of the slope. So we'll add to that and say the car's speed is not constant, or we could say that the car accelerates as it goes down the slope. Now you've got to describe how the student could take measurements to find the speed at the bottom of the slope. So here we go, we've got our car going down the slope. Sorry about my dreadful drawings again. We don't want to know its average speed over the whole journey. We want to know its speed right here at the end. Okay. Now what we'd really like to do, okay, is to get ourselves a distance time graph to look at how the speed increases as it goes up. Okay. And the best thing to do really is to find the gradient at the end of the track. If we know that gradient, then we can work out the gradient from there, and that will give us the speed at an instant in time. Okay? But we need measurements of distance and time to do this. Now we can't get these measurements very easily from using a stop clock and a meter ruler, but there are a few ways we can use it. Now one way that we looked at was using ticker tape, okay, and a ticker timer. This allows us to get data on the time, so we're looking at the time here that it's taken, the distance it travels in each unit of time. Another way is to talk about using light gates, where we might place one light gate right at the bottom. We might place a light gate right here, and as the front of the car goes through it, it should start a timer. As the back of the car goes through it, it ends the timer. And once we've got that distance here between them, and we know the time it's taken, then we can work out an instantaneous speed that way. Another possibility as well is that you could video what was going on, and if you've got a sensitive enough video camera, you can analyze the time it takes to go a very small distance towards the end of the slope. But you need here to be given something more than just saying we're going to measure a small distance and we're going to time it. If you look at the mark scheme for this question, it's at 3 marks. They could give 3 marks for using light gates, you can get 3 marks for using ticker tape, you get 3 marks for using video camera, or you could use a motion sensor like the one we've used as well. But the key thing is that you explain how we use each of these pieces of equipment to get the data we want. We don't want an average speed, we want a speed at an instant in time as the car gets to the bottom of it. The student then repeats the experiment using the same equipment and the same starting height. She finds that the time taken for the car to move down the slope is not exactly the same for each experiment, and you need to give 3 reasons why. Now we can't just say, oh, it goes at different speeds each time, okay? If everything is the same in both repeats, we would expect it to go at the same speed. So you need to give a reason for why the speed might differ. Now the kind of things we're looking for here are errors in timing, and we want to try and be specific with this, that's starting and stopping the stop clock. But we may not be able to start it and stop it exactly the same every time. Even if the car moves in the same way every time, our human kind of reaction times is affecting the time we get. It could be that each time we release the car, and we don't release it exactly the same. Maybe sometimes we accidentally apply a little bit of force in the direction of the slope. Maybe sometimes we apply a little bit of force in the opposite direction. So we could say that the car is pushed at the start, or that the release is not exactly the same each time. We could also add that maybe on some occasions the car moves in a straight line right down the slope, while at some on other repeats of it, it goes at an angle down the slope, so it's following a slightly different path. So the car does not run in a straight line, or even the car hits the sides of the ramp. And if that's the case, then obviously that's going to increase the size of the frictional force between the car and the ramp.